In this video, we will talk about some properties and definitions for different processes with their density, their mean, autocorrelation, and autocovariance functions. The first one is for the Poisson process, which is also a Poisson counting processes. It defined on a number of lengths from T1 to T2, at which the time is equals to k, and the probability density for it follows the Poisson distribution, which has the e to the power of lambda t times lambda t to the power of k divided by the factorial of k. And for the intervals from T1 to T2, and if we have another interval from T3 to T4, and if these intervals are not overlapping, then the random variables for in the Poisson process are independent. So it follows the independent increment process. And for its first order density, which we will consider the time is on a certain time as the st. So the probability for st equals to k follows the Poisson distribution. And its mean for the expected value for xt is the same, came from there also as well. So it's lambda t, and its autocorrelation from T1 to T2, it is equals to lambda square times T1 times T2 plus lambda to the mean and times to the mean of T1 and T2, and its correlation autocovariance is lambda square T1 T2 plus lambda mean lambda times the minimum of T1 and T2, then minus lambda T1 times lambda T2. So this one is same here. So the correlation is only equals to lambda minimum T1 to T2. So since we can also see the estimation of its the Poisson process follows the linear linear function. So we can see that if we have longer time to wait, the estimation will be longer. And because of this definition is independent. Increment follows the independent increment process. And second, for the Poisson increment process, it defined as the process by, if we have a process yt, then the time. Then if we have the process xt, which is a kind of the Poisson process, then the yt is, if the yt is equals to x, the process from a certain time plus a difference minus xt on the certain time divided by the difference of the time epsilon. If we follow this, it is called the Poisson increment process. And for its first order probability masses, it equals to the, if yt equals to a certain time, which is n divided by the time difference, it is equals to the time. It replaces the time from t to the time difference as the e to the power of lambda epsilon times lambda times epsilon to the power of n divided by n, the factorial of n. Then for its minimum is equals to lambda, which is a constant given in the function. And for its autocorrelation, it is equals to lambda to the power lambda square when the time difference when with the given difference is larger than what we have for the epsilon, and equals to lambda square plus lambda divided by the epsilon minus lambda times the time difference, absolute value of the time difference divided by epsilon square. And that is happen when the difference is less than epsilon. Also, the autocovariance. If we have the difference larger or equals to epsilon, it equals to 0. And also, if difference less than epsilon, the autocovariance is equals to lambda divided by epsilon minus lambda times the absolute value of differences divided by epsilon square. And if we can, as we can see the functions here, if the absolute difference is getting closer to zero, and the triangle value, triangle for the Poisson increment is more closer to an impulse on the certain time. Third one is for the Poisson impulse process. It defined as if we have a Poisson process xt, then its derivative on the times is we call it zt, and the zt is kind of the point impulse process. And here, which means on certain time, if we used to have some triangles, but now we only have some impulse on the certain time. And because of this, because it's kind of the impulse process, so its probability masses cannot be defined. And the estimate value is equals to the length here, which is the lambda, and the autocorrelation is equals to lambda square plus lambda times the impulse T1 minus T2. This one is called Ti. And also the covariance is equal to lambda, only this part, so it's lambda times impulse T1 minus T2. And for the semi-random telegraph signal, it defined based on the Poisson points again. It came from the Poisson, which is on n times number from T1 and T2 equals to k equals to E lambda T lambda Tk times tan k. And we have some random values for for xt when has two different probability, when k is even, and for negative 1 when k is odd. So if we replace has this process and replace it into the Poisson, we can have the probability density masses is on the first order is equals to when xt equals to 1 and is plus and is e to the power of negative lambda times t times e lambda t plus e negative lambda t to the power of 2 divided by 2. And when it's negative 1, just replace the plus into negative into minus. And it means if we have times 1 and times negative 1, then add them together. So we will divide it by 2, and it will receive the e to the power of negative 2 lambda t. And its autocorrelation still replaced by the difference. It is e to the power of negative 2 lambda times the difference of absolute value. And also for the autocovariance is equals to e to the power of negative 2 lambda times the absolute value, then minus e to the power of 2 lambda times the summation of t1 and t2. Then if we can see the correlation and the covariance and the correlation, we can see that if T1 and T2 goes far away, then their difference here will be much more larger, and then will be much more less related. The fifth one, for the random telegraph signal, we still have the the probability on 1 and negative 1. But at this time, finally the probability are the same, so so both on 1 and negative 1 is equal to 1 over 2. Where xt is kind of the semi-random telegraph signal, as we mentioned before. And at this time, since the probability are same, we can when we try to find the estimation, and they will come up to 0. And for the autocorrelation, we can just replace by, we don't have the summation here. And finally, they both are e to the power of negative 2 lambda times t1 minus t2, so absolute value. And we can see that since the estimation is 0, and even if we add time difference for some certain value as the epsilon, the time is still same follows the p equals to 1 and e equals to 1 on the different time, and it's still same. So follows the even and odd. So at this time we can imply that the random telegraph signal is a kind of the strict sense stationary process. For the sixth one, the random walk. If we toss a fair coin n times, k is number of heads and n is toss. So we can have a kind of the signal process is t times x to the nt is equals to ks minus n minus k times s equals to 2k minus n s, where n is the number of times, k is the number of heads, and n is in the n is what we toss times. So basically, we came out this formula with how many pickups that we can receive the result what we expected. So the first order probability First of all, the probability method is come up follows the same process. It is equals to, if we define it as xt, then xt is equals to this, the tosis with the times, equals to some what we expected result is equals to n, then pick up n plus 2 minus n plus r minus 2, and times 1 over 2 to the power of n, which means the probability we receive the head or tail. And for the time is time in the range is equals to n times t and n plus 1 times t. Its expected value is equal to 0 since the head, both head and the tail has the same equality, so they add them together and didn't have more respected value. And for the correlation, it equals to since they are independent, and they will become the two process multiplication together, and then replace them together, and as we pick up the minimum from n and m, which is two kinds of the toast time, and then times s squared, which means for this. And also for the covariance, the same we can find it still with the minimum from n to the power to m, and then times s squared. If the n goes infinity, then the density will be more like a Gaussian density. And the minimum from here, because the toast time may be increased, so it follows the independent increment. Based on the time is not overlapping, so a correlation function contains the term here can imply to the independent increments. The seventh one, the winner process. If we have we define it as the elimination of xt, where xt is kind of the random walk here, and when the time is more close to 0, and s divided by t is equals to kind of the constant a. Constant alpha a, and times is more close not close to infinity, so then for its first order density function is equals to 1 over square root of 2 pi alpha t times e to the power of negative w squared divided by 2 alpha t, which is more like a Gaussian distribution. And still, because the elimination doesn't really affect the expected value for the two kinds of output, so the expected value estimate is still 0. And for the correlation, we don't have the effect for the s, so finally its correlation and covariance is equal to the minimum of the t1, t2 times and times the alpha, which is